Earthquakes are some of the most dangerous natural disasters humans have experienced. They often come with little warning and can cause serious damage. Buildings collapse, roads cave in, and landslides tumble downhill during an earthquake. People may be trapped in their homes or under debris, and the cost of rebuilding after such an event can be tremendous. An earthquake is not one isolated event. However, much of the ground shaking that comes from an earthquake, which is the shaking of the ground when rock below Earth's surface breaks, comes in one large burst of energy. This is similar to a spring recoiling. When you push the spring together on itself, it builds up energy. When you let go, the energy explodes outward in all directions from the center point. The same thing happens underground when rock is stressed along plate boundaries. Rocks may be compressed when they're pushed together, experience tension if they're pulled apart, or generate friction if they're rubbed along each other. If you have a bad day and the stresses just keep building up all day long, you're likely going to snap at some point. The stress becomes too much to bear and you explode when you reach a breaking point. Rock underneath Earth's surface does the same thing along faults. These are fracture lines along broken rock that move. Movement along faults may not cause an earthquake, but if the movement builds up enough energy, the stress causes the rocks to reach their breaking points and release that energy as an earthquake. Because faults are not straight, smooth boundaries, ground shaking often occurs both before and after the main quake. Foreshocks are the energy release and ground shaking before an earthquake, and aftershocks are the energy release and ground shaking after an earthquake. Foreshocks are before, aftershocks are after. Makes sense. Foreshocks are less likely to do damage than aftershocks because they're smaller in magnitude. You might even think that they could be used to predict earthquakes, since we can measure seismic activity, the movement of ground, on a machine called a seismograph. Unfortunately, foreshocks are usually too small and too close to the time of the main quake to help us know that the main quake is coming. Aftershocks are sometimes just as hazardous as the main quake itself. In fact, aftershocks may be so strong that they're stronger than the main quake. When this happens, the aftershock will be renamed as the main quake, and the main quake will be considered a foreshock. While foreshocks occur around the same time of the main quake, aftershocks may not occur until days or weeks later. Aftershocks are fairly unpredictable. The main quake doesn't tell us much about an aftershock. We don't know if or when it will come, where it will occur, since it doesn't always occur in the same place as the main quake, or how strong it will be. Aftershocks may continue to do damage to an area that has been hit by the main quake because structures like buildings and roads are already rattled from the previous shaking event.
Earthquakes can cause huge amounts of death and destruction. For this reason, understanding them is vitally important. Like all major events, seismic or otherwise, they have to start somewhere. The epicenter is the place on the Earth's surface under which they start. There are two important locations in any earthquake. The most important is the hypocenter, or focus of the earthquake. This is the point where the earthquake truly begins, deep under the ground and located at a tectonic plate boundary, the border between two of the fragments the Earth's crust is broken into. It is where the plate boundary begins to rupture. The epicenter, on the other hand, is the point on the Earth's surface directly above the hypocenter. This is a more useful measure for human reporting because it can be shown on a map. The epicenter is usually the location where the waves from an earthquake are most intense, and as a result, it is also the location with the most damage. But this isn't always true. If an earthquake is particularly large, it may run across a large section of the plate boundary. In this case, the epicenter might only be one of many hotspot locations, and damage could be greater elsewhere. In a 2002 Alaskan earthquake of magnitude 7.9, the greatest damage was 330 kilometers away from the epicenter. The epicenter was at the western edge of the rupture, but more damage occurred at the eastern edge. Scientists have come up with a number of ways to figure out the location of an epicenter. The simplest requires the positioning of seismographs, equipment that measure the strength of ground tremors and earthquakes around the area. It is possible to use a process of triangulation to figure out the location of the earthquake. This hinges on the fact that there is a lag time between receiving the first waves of an earthquake, called the P waves, primary waves, and the latter S waves, secondary waves. Since we understand how these waves work, we can use this lag time to calculate the distance from the earthquake to the seismograph. Larger distances mean greater lag times. Then, by drawing a circle around the seismograph on a map that represents the distance, you can narrow down the location. 3 circles from 3 seismographs will overlap at the location of the epicenter.
An earthquake is just what it sounds like, the quaking of Earth. The ground shakes and moves due to rock breaking below the surface. This movement of ground is called seismic activity. And while we can't always tell when, where, or how strongly an earthquake will hit, we can measure its magnitude while it's happening. In 1935, Charles Richter developed the local magnitude scale, a scale used to measure the magnitude of earthquakes. Now called the Richter scale, these measurements tell us how much the ground shook during a quake and how much energy was released. This information comes from seismographs, which collect data and directly measure the amount of ground shaking. The Richter scale runs from 1 to 10, 1 being the least in magnitude and 10 being the greatest, but it is logarithmic. This means that for each 1 point in increase on the scale, we get 10 times more ground shaking. Let's look at an example. Say we have a magnitude 1 earthquake on the Richter scale, which is the lowest magnitude earthquake. Compare that with a magnitude 2 earthquake, which is only 1 step higher. Remember, the scale runs from 1 to 10, and you now have 10 times more ground shaking than with the magnitude 1 quake. Take another step up the scale, so from magnitude 1 to magnitude 3, and this is 10 times more than that first step, so we now have 100 times more ground shaking with just 2 steps up the scale. That's a lot of seismic activity. Now let's see how this relates to the total energy released during an earthquake. Through measurements of seismic activity, scientists know that the energy released by an earthquake, which is what causes all that shaking and moving in the first place, increases 32 times for each step up the Richter scale. Take our example from before where we have a magnitude 1 and a magnitude 2 quake. The magnitude 2 quake will have 32 times more energy than the magnitude 1 earthquake. Now let's compare our magnitude 1 and magnitude 3 quakes. The magnitude 3 quake is 2 steps up the Richter scale, so we have 32 times more energy for the first step, and then 32 times more energy than that up the second step. 32 times 32 gives us about 1,000 times the energy with just 2 steps up the scale. This is even more amazing when you compare this with the difference in ground shaking. A magnitude 3 earthquake has 100 times more ground shaking than a magnitude 1 quake, but about 1,000 times the energy. That's a big difference. The Richter scale was originally designed to measure medium-sized earthquakes, those between magnitude 3 and 7, and within a distance of about 400 miles. The moment magnitude scale was created in 1979 to deal with these issues, but it built on the Richter scale because it was already so accurate for small to medium-sized quakes. The moment magnitude scale is the currently accepted scale used to measure medium to large-sized earthquakes. The Richter scale remains the standard for quakes smaller than 3.5 in magnitude, and luckily, this is where most earthquakes fall on the scale. About 1 million magnitude 2 earthquakes occur each year, compared with only about 1,000 magnitude 5 quakes. Magnitude 10 earthquakes are extremely rare, occurring less than once a year. Considering that the energy release of a magnitude 2 quake is equal to about 50 kilograms of explosive, while a magnitude 5 releases energy equivalent to 1,800,000 kilograms, we should be very thankful that they are so infrequent. Earthquakes are one of the most dangerous natural disasters that occur on Earth. This is because the shaking of the ground can strike with little to no warning, and sometimes the ferocious ground shaking can even be felt hundreds of miles away. Have you ever thrown a rock into a pond and watched the ripples travel outward? Anything that is in the path of those ripples gets disturbed, like bugs lounging on the surface and plants poking their heads out from under the water. Even the shoreline gets disturbed once the ripples make their way to the edge of the pond. Earthquakes have a similar effect on objects above Earth's surface. Anything that is near where an earthquake occurs is likely to be affected. Some of the effects are immediately seen, while some are more long-term. Because an earthquake is literally the quaking of the earth, you can imagine that anything on the surface that is near the shaking will shake as well. Remember how your mother asked you not to run in the house? This is because if you run into something like a china cabinet or a bookshelf, you could knock the contents loose. By bumping into the shelving, you shook everything that it was holding. Earthquakes have the same effect on land. Landslides and mudslides are common events during an earthquake because the ground is shaken so much that it gets knocked loose and slides downhill, taking anything else down with it. Trees, houses, power lines, and anything else along the hill gets brought down when the land or mud comes sliding down. This is not only dangerous for people whose houses get destroyed, but it also destroys the habitat along the hillside and at the bottom. Liquefaction is another type of damage caused by earthquakes. This is when water-saturated sediment moves and acts like a liquid. You may have experienced this standing along the edge of a beach when the surf comes up. As the water comes up around your feet, it soaks the sand underneath, which then starts to move like a liquid instead of solid ground. During an earthquake, the ground shaking loosens moist soils in the area, which separates the particles, and the ground begins to act like a fluid. Liquefaction is very dangerous because the flowing ground can swallow up entire buildings and roads. Tsunamis are large sea waves that arise from ocean earthquakes. Tsunamis are not just larger versions of ocean waves and are often like a large rising tide. They can be tens of feet high and wash over large areas of coastal land. The 2004 Indian Ocean tsunami is considered one of the deadliest natural disasters in history because it killed over 200,000 people in 14 countries. Just like the books on the bookshelf or the dishes in the china cabinet, anything attached to the shaking ground is also going to shake. Buildings, roads, power lines, and other human-made structures are at risk for damage when an earthquake hits. Earthquakes themselves rarely kill people. It's the collapsing buildings that tend to be the deadly factor. Items inside buildings fall on top of people, building structures come loose, and many times buildings simply collapse to the ground, killing those who may be stuck inside. Because earthquakes do not generally give us much warning when they're coming, people often do not have time to escape. Roads may also collapse, or they may be covered by debris from landslides or sucked into the ground by liquefaction. Bridges are especially at risk because they are supported above ground and are not as stable as roadways that are directly on the surface of the ground. Fires are quite common during earthquakes as materials in the debris from falling buildings and roads can be flammable, power lines get torn down, and electrical wiring in houses becomes exposed. These fires are very dangerous and can spiral out of control if firefighters can't access them due to collapsed roads and other structures. Structural damage also leads to economic damage. Cleaning up debris, rebuilding roads and buildings, and searching for missing persons can all put enormous financial strain on cities hit by earthquakes. And considering that some of the most populated places have the most earthquakes, like California and Japan, earthquake damage and destruction must often be accounted for not just once, but over and over again.